Good morning. In this session, I would like to demonstrate the use of optimization toolbox in Aspen. In fact, a similar problem has been worked out with the help of design spec and calculator block. Though the reaction and the kinetics are different, the problem is more or less similar. We wanted to make use of two CSTRs connected in series of equal volume. In order to get 95% conversion, we need to find out what is the minimum total volume of the two reactors. Let us see how to handle this problem and solve it using optimization toolbox. So first step is we need to define the state. Let me name it as ED. Then the other compound is methyl acrylate. It as MA, and then acetic acid. These are the three components that we are going to make use in this problem. Let me call it as A. Having defined the components, now go to the next step, choose a property model, and then go to simulation environment. Your flow sheet. So we are using two CSTRs connected in series. Then connect the input and output streams to complete your flow sheet. So having done this, now we will proceed with defining the problem. So we know these are the conditions given in the problem statement. The reactant is entering at a temperature of 800 Kelvin and 5 atmospheres. Pure reactant is entering at the rate of 1000 lb per hour. In the state, it is entering at the rate of 1000 lb per hour. Right? So we have defined stream 1. We need to define the blocks. So the block is also operating. Each of the reactors are operating at the same temperature and pressure, which is 5 atmospheres and 800 Kelvin isothermal. You know this is vapor only. So let me assume the volume of the reactor as 10 liters to start with. Go to the next. Now we need to talk about the reaction. And I am choosing power law model because it is first order irreversible reaction. So next, similarly you define the conditions for the second reactor as well, which are similar to the first reactor. Again, I am assuming the volume as 10 liters. Next. So I will use the same reaction. Okay, next. Now we need to we know the stoichiometry. Ethylene diacetate, it is first order with respect to the reactant, methyl acrylate and acetic acid. So we have defined the stoichiometry. Now we need to talk about the kinetics. You know this converted into vapor. This is 7.8 into 10 power 9. So the moment you don't specify the temperature, this will be taken as A. T0, if it is not mentioned, we are going to make use of the second equation to calculate the rate constant at any given temperature, provided we supply A and E. So by default, if you are using Arrhenius law, N is taken as 0. So the value of activation energy is given to be 38,200 calories per mole. So we have defined this kinetics. So we should be able to run it initially. Now you can look at the stream summary. For example, if you look at this, now we have 3.1 kilomoles per hour of the reactant is entering. At the end of the first reactor, we got some conversion. And similarly, at the end of the second reactor also, we got to some conversion. Now, if you want, conversion is something we did not get whatever is the required conversion. We will probably will have to use to obtain the required conversion of 95%. Problem using a design spec along with a calculator block. Now we would like to use another tool to solve this problem. Now let us use expand model analysis tools, optimization, say new. It labels it as O1, optimization 1, okay. Now, what is that we want? We wanted a particular conversion. So how will you be able to define conversion? Let me define two variables, FA naught, the inlet molar flow rate of the reactant. It's a stream variable, which is mole flow of in stream 1, inlet stream of this particular component. So this variable is going to represent the inlet molar flow rate of the reactant. Similarly, I would like to define another variable FA, which is the molar flow rate of same ethylene diacetate from the second reactor. Mole flow exit from the second reactor is S3. So they are going to represent the inlet and outlet molar flow rates. Sorry, this probably we need to talk about this in not here in conversion. So sorry. Now, whatever variables that you want in your objective function must be defined here. Let me define the volume of the first reactor V1, which is a block variable. Block is V1, variable is volume. Similarly, define the volume of the second reactor V2. It is also a block variable. Block is second V2 and volume. Status. So go to the next. In other words, you need to define all the variables that are going to be included in your objective function. We wanted to minimize the sum of these two volumes, V1 plus V2, right? The constraint part later. How will you be able to do this? What is the constraint that we have? Let me address this constraint first. Say new. We wanted to obtain a conversion of 0.95. So this is where we need to FA naught, which is the molar flow rate of ethylene diacetate in the input stream, which is S1, variable is, component is ED. Similarly, define the molar flow rate of ethylene diacetate in the exit from the second reactor. So this is again mole flow. Exit from the second reactor is stream S3, component is ED. So these two variables are going to represent the molar flow rate of the reactant at the entry and exit. Now let me go to the next. We know the conversion is defined as FA naught minus FA divided by FA. So this should be equal to point with some tolerance, right? So we have defined the constraint. Now I will complete the optimization definition. So you can see the constraint is defined. You need to bring it to the right hand side in order to force it. The required conversion. Remember, we started with an assumption for the volumes of both the reactors as 10 liters. Now, by varying the volumes, we need to get to the required conversion. At the same time, we need to minimize the sum of these two volumes. So let me go to the next step. Say new. Unlike the case of design spec, in the case of optimization, I'll be able to vary as many variables as I wish. So earlier we were able to vary only one of the reactor volumes, whereas here I'll be able to vary both the reactor volumes. Let us say 10 to maybe 1000. And similarly, say another new. So this is also, I'm going to vary like what I did with V1. Again, 10 to 1000. Now, the limitation with the design spec is we will be able to vary one of the variables, whereas in optimization you will be able to vary as many variables as you wish. Now, we are trying to vary the volumes of both these reactors and also minimize the sum of these two reactor volumes in order to get a conversion of 95%. That's what we have specified. That is the constraint. So let me run this problem for the time being. So we got to the method used by default by Aspen is SQP, sequential quadratic programming. We were able to come to the results. See, Let me look at the result of the constraint. So you can check it up. 3.1, the outlet flow rate is 0.15. So we can probably check it up by using a calculator. So 3.10 6 minus the outlet flow rate is 0.155224 divided by 3.10376. So we got to 95% conversion within the tolerable limit. So we were able to satisfy the constraint. We wanted to get 95% conversion, which has been achieved. But what about the optimal result? We got to a total volume of about 513 liters, and the volume of the first reactor is 239, whereas the volume of the second reactor is 274. However, you can see from the problem statement that we need to use two equal volume CSTRs. This part was not yet addressed. Let us see how to address this as well. Now, we were varying the volumes of reactor 1 and reactor 2 independently. Can we make that as equal? So that can be done by forcing another constraint, say mu. Now, again, define all the variables involved in this constraint to make sure that it is not going to conflict with the variables defined in the objective function. I am using VO1 as the volume of the first reactor, V1. Again, the variable is volume. Similarly, I would like to define VO2, volume of the second reactor. It's also a block variable, like what I did in the earlier case. V2 variable is volume. Now, what is the spec? The spec means we cannot equate one variable with another variable, but we will be able to write like this: VO1 plus VO2 should be equal to 0. In other words, we are trying to force the volume of these two reactors to be equal. So once again, go to this optimization input. You can see constraint 1 was effective earlier. Now we have created another constraint. I am going to bring it to the right side in order to force it. Now we are trying to minimize the sum of these two reactor volumes under two constraints. One constraint is going to 25% conversion. The other constraint is going to force make both the reactor volumes as equal. So with this modification, let me run the problem again. So there was some issue with respect to convergence, but let us see the result. We were able to get to the required second. So we have 256.6 plus 256.6. So these were the two earlier volumes that were found out. You can see we were more or less at the same total volume, but we were able to come to the conclusion that these are the two equal volume reactors required to obtain the required conversion. This result, I think it has not come to a convergent solution. Probably that should not be a major issue. Maybe you can increase the number of iterations and see whether to reach the convergent solution or not. So in this way, you should be able to use even an optimization tool to solve such problems. Maybe we will try to do examples under optimization at a later stage. With this, I would like to close the session.